Welcome, everyone, to today's Explainer. Right now, we're laying the absolute groundwork for understanding how massive, incredibly complex industrial systems manage to operate seamlessly without, tearing themselves apart. We're diving into the foundational concepts of process control. And honestly, whether you're dealing with a bioengineering lab or a massive oil refinery, the principles we're covering today are the invisible forces keeping everything running. I want you to think about this question for just a second. How do you safely control a chemical plant that is running 24/7? The stakes here are just incredibly high. Modern process plants are massive, highly integrated facilities handling hazardous materials, complex chemical reactions, and extreme temperatures. We're literally talking about keeping a beast under control every single second of the day, ensuring it absolutely doesn't overheat, overflow, or shut down. Okay, let's dive into this. Here's our agenda for today. 1. Welcome to control. 2. Control objectives. 3. The process triad. 4. Real-world examples. And 5. The big picture. Let's start with Section 1. Welcome to control and how we go about preventing chaos. So, process plants operate on an immense, continuous scale. They definitely do not run on a cozy 9 to 5 schedule. We're talking 24 hours a day for 330 days or more every single year. And during transients like startups, shutdowns, or unusual disturbances, the system is highly vulnerable. Without continuous computer-based automatic control systems constantly comparing measurements and making adjustments, well, it would be physically impossible to operate these massive plants safely and profitably while also satisfying strict environmental requirements. Moving right along to Section 2, control objectives. Basically, why do we even need process control? Well, an immense responsibility rests on the shoulders of process control. At a high level, we really have two primary reasons for doing this: to stabilize and optimize process plant yields, and to ensure that production processes are safe and environmentally friendly. This translates to very tangible objectives. We want to increase product throughput and the yield of our higher valued products, but at the exact same time, we must decrease energy consumption, cut down on pollution, and reduce off-spec products. And, above all else, we absolutely must guarantee safety and extend the life of our really expensive equipment. Which brings us to Section 3, the process triad. These are the three main variables we deal with. First up in this triad, we have controlled variables, or CVs. These are the process variables that we actively want to control. Think of things like compositions, temperatures, and pressures inside a reactor. Our primary mission is to maintain these variables at a specific desired value, which we call the set point. Next up, we have manipulated variables, or MVs. So the crucial point here is that these are the actual levers we can pull. These are the variables that are adjusted in order to keep our controlled variables at or near their set points. In thousands of industrial applications, manipulated variables are typically flow rates. We adjust them using physical equipment like control valves or variable speed pumps. Finally, we have the troublemakers of the group: disturbance variables, or DVs. These are the process variables that affect our controlled variables, but, and here is the kicker, they literally cannot be manipulated by us. They're generally related to changes in the operating environment. This could be a sudden change in ambient temperature outside the plant, or maybe a change in the crude oil composition feeding into our system. They act on the system, and our control system just has to react to them. Let's put this into practice with Section 4, real-world examples, taking theory into practice. And honestly, this brilliantly illustrates everything we've just discussed. Take a continuous stirred tank reactor, or a CSTR for short. As you can see, there's the mixer inside, the heating coil at the bottom, and the feed streams coming in and out. In a single unit like this, multiple variables are interacting all at once. You have an inlet stream bringing in materials at a certain temperature, a heater adding energy, and a liquid level to maintain. Let's break down exactly what happens if the chemical reaction inside that tank is highly exothermic, meaning it produces a ton of heat. To prevent a total disaster, we absolutely must control the reactor temperature. That temperature is our controlled variable. How do we do it? Well, we manipulate the flow rate of a coolant running through a jacket or cooling coil around the reactor. That coolant flow is our manipulated variable. Meanwhile, the feed conditions coming into the reactor, like if the flow rate suddenly drops or the composition changes, those act as our disturbance variables, constantly threatening to throw our reactor temperature off its set point. To really consolidate what we've learned, we can see how universal this triad really is across the board. It's like a universal language. It doesn't matter if you're looking at a blending system, the CSTR we just analyzed, a thermal cracking furnace breaking down crude oil, or literally a medical kidney dialysis unit. They all rely on the exact same logic. In a thermal cracking furnace, we want to control the furnace temperature, the CV, by manipulating the fuel flow rate, the MV. What throws it off? The crude oil composition, the DV. In a kidney dialysis unit cleaning a patient's blood, the blood flow rate is maintained by a pump, but ambient conditions act as disturbances. The framework remains perfectly consistent across wildly different applications. Let's zoom out for Section 5, the big picture, looking at plant-wide control. Now, what's really interesting here is the story told by a fluctuating process variable. If you look at this, it's bouncing wildly, perilously close to an upper operational limit. This limit might be an equipment constraint, like a metallurgical limit, or a safety constraint to avoid a runaway side reaction. Unmanaged disturbances push systems to these dangerous limits. This is exactly why process control has to step in, to smooth out those fluctuations so we can operate safely and, crucially, so we can operate as close to the optimal limit as possible without crossing it. Because once we have that baseline control, we unlock a much larger structure, the hierarchy of process control. At the absolute foundation, level 1, we have measurement and actuation, sensors and valves operating in fractions of a second. Level 2 ensures safety and equipment protection. Level 3 is regulatory control, which includes the feedback and feed-forward systems keeping our controlled variables right at their set points. But look what happens when we master those basics. We unlock levels 4 and 5. We gain the ability to run real-time optimizations and plant-wide scheduling over days and months. Mastering the micro-variables unlocks the macro profitability and safety of the entire operation. Which leaves us with a fascinating, pretty provocative question to end on today. Through our process variable triads, we know exactly what to control, what to manipulate, and what to watch out for. But how do we actually control it? I mean, how does the system automatically know exactly when to open a valve and by how much? That question sets us up perfectly for our future explainers, where we'll dive into the incredible mechanics of feedback and feed-forward control systems. Thanks so much for joining me on this explainer, and keep questioning how the complex world around you is controlled.